Okay. All right. Good afternoon or good evening. So our next talk is by Elisa Lorenzo García from University of Neuchâtel, and she'll talk about primes of bad reduction for genus 3CN curves and their exponents on the discriminant.
Thank you very much for the introduction, and thank you very much for the invitation. I'm very happy about being able to share my results with all of you. So, I mean, the title of my talk, maybe, I don't know, maybe there are like many technical words, but I mean, don't worry, I'm going to try to explain everything and to motivate why I'm interested in this primes of bad reduction, and particularly today in the exponents of those primes in the discriminant. So, I mean, as you can see, there are many authors in this work that I'm presenting today. And basically it is because this is a follow-up paper from a Women in Numbers conference that happened in 2016 in Leiden. Actually, Rachel was one of the organizers. So, I mean, this is a follow-up paper from this conference. And even I can say that the project in this conference was like a follow-up project from another Women in Numbers conference, like in 2013. So, I mean, this is why there are like so many authors. Okay, so I'm going to start really with an introduction, a motivation to the problem, why I'm interested in this thing. And my motivation is the following. It's the complex multiplication method. What is the complex multiplication method? Well, it's a method that is useful for solving the following problem. So, I mean, of course, here I'm taking like particular numbers, but I mean, it works in general. So the problem is the following. We fix a prime number. In this case, I fixed p equal to 70. And what we want is to construct an elliptic curve over this finite field, fp with the p that I took, such that the curve has a given number of points. So, I mean, the number of points of an elliptic curve. Oops. Can you see the mouse when I move it? Well, I hope you, well, it's not a big thing if you can.
I can.
Yes. Yeah, okay, good. Thanks. So, we know that the number of points of an elliptic curve over a finite field is given by this formula, that is p plus 1. Even I could have written here q a power of p, but I mean, it's not a big thing. So p plus 1 minus the trace of the Frobenius. This a is a trace of the Frobenius. So basically, if we want, and in this example, to construct an elliptic curve over f17 with 22 points, okay, what we need, or this is what the complex multiplication method tells us, is that what we have to construct is an elliptic curve with an endomorphism, the Frobenius, that has norm equal to p, 17, and trace equal to -4. That this is what we want to have here, the equality to 22. Okay, but constructing an endomorphism with these properties is kind of equivalent to say that we want to construct an elliptic curve with an endomorphism ring isomorphic to this O that I presented here. So what do? We take O equal to Z and we add this element. Who is this element? This element is going to be like the Frobenius because it has trace equal to A, and the norm, we are going to force it to be equal to P. And this gives us this condition in D. So we need D to be this number. So, okay, this is the idea now. We wanted to construct this elliptic curve with this given number of points. Then we decided that this is equivalent to construct an elliptic curve with an endomorphism with this norm and trace, and that this is equivalent to construct an elliptic curve with endomorphism ring isomorphic to this order in this imaginary quadratic field. So how do we do this? Well, for this, we define what we call the Hilbert class polynomial. So this polynomial that I call HOT, because it depends on the order, basically is a polynomial whose roots are the Egusine variants of elliptic curves, attention, defined over the complex numbers, and we will see why, that has complex multiplication by O. So, I mean, basically what we are looking for is one of the roots of this polynomial, right? If we want to look for an elliptic curve with this endomorphism ring. So, okay. Different things. First, this polynomial, I define it with the elliptic curves defined over the complex numbers. So, which is the strategy? I compute this polynomial that, I mean, a priori should have like complex coefficients, but no, it's great. We have like even integer coefficients. Oh, sorry, this is not a parenthesis. This is like, I mean, really polynomials. We get polynomials with integer coefficients, which is great. I mean, it doesn't matter the order that we take, we get integer coefficients. But the curves are complex elliptic curves, but I mean, if I get something with integer coefficients, I can do the reduction modulo P. And actually what happens is that these elliptic curves, because they have complex multiplications, they are not only defined over the complex numbers, but over a number field. So I can do the reduction modulo P. So this is the idea. And how do we construct those polynomials? So I mean, this is the key for the complex multiplication method. Well, the idea is the following. As we saw in some talks today and yesterday, we have an expression for the invariant of an elliptic curve, like a complex elliptic curve. So our complex elliptic curve, we can see it as a complex torus and somehow parameterized by a tau in the upper CL upper half plane. So, I mean, we just, computing the taus that corresponds to elliptic curves with Cn by a given order, this is easy. We also saw this in a talk yesterday, I think. So, I mean, we can compute those taus. And now we have for the J invariant and a development of this J invariant as a series in terms of tau, or Q, or Q. I'm going to give the formula later. So the idea is that we can approximate the value of these J invariants. But now, because I know that this polynomial has integer coefficients, if I approximate with enough precision, I can get the exact value. I mean, if I get 2.99 and I know that the precision is very high, then this must be equal to 3. So in this way, I can approximate the coefficients and I can compute them. So, I mean, keeping with the example, I mean, well, actually this algorithm that I just described, this is even now implemented in SATE. So you just can ask SATE for the Hilbert class polynomial. And I mean, this is what I did for this example. And of course, I directly took the reduction modulo 17 of this polynomial. In this case, it's a polynomial of degree 2. So now if I want to construct an elliptic curve with this number of points, I just take one of those J invariants. So I took the J invariant minus 12 that corresponds to this root of the polynomial, and I constructed an elliptic curve with this J invariant. I mean, this is easy. There is like a classical formula that given the J invariant, you can pick an elliptic curve with that given J invariant. And I mean, now I was lucky and I got the right number of points. Why I said I was lucky? Because I mean, actually, I mean, if I would have taken, I mean, if I took the quadratic twist of this elliptic curve, then the trace of the Frobenius is minus the trace. But well, I mean, this is not important. I found the elliptic curve that I wanted. And I mean, I know how to do it. So this is a description for the complex multiplication method. So now, of course, the idea is that I want to generalize this for genus 2, genus 3, or higher genus. So before doing this, I need to give you like some definitions, previous definitions. So I'm going to start with the definition of a complex multiplication field. So what is a complex multiplication field? It is an imaginary quadratic extension of a totally real field K plus of degree G. So for the elliptic curves, G is equal to 1. So I mean, this is Q. So it's just an imaginary quadratic field. And then, well, some notation I'm going to take to work in general with an order in this complex multiplication field. So I mean, I think that with this tower of fields, we see what is this. So basically, first we take here an extension of degree G, totally real. That means that all the embeddings of K plus into the complex number are actually into the reals. And then I get a quadratic imaginary extension. So this is a complex multiplication field. Now we say that a curve of genus G has complex multiplication if its Jacobian has complex multiplication, meaning that actually there exists an embedding of the order O in the CM field K into the endomorphism ring of the Jacobian. And I mean, well, we ask the embedding to be optimal. This is like a technical condition. We don't really need it now. So, I mean, this means having complex multiplication, means that you have a lot of endomorphisms. And I mean, some of them, well, nice ones. Very well. Now I define, after the definition of complex multiplication field, I'm going to give you the definition of complex multiplication type. So basically, K, we have 2G, the degree of K over Q is 2G. So we have 2G embeddings of K into C. Now, these embeddings actually came in pairs, because each time that we have one embedding, we have the conjugated one, because of this quadratic imaginary extension of degree 2. So a CM type is just a choice of G embeddings such that they are not conjugated one. So basically, for each pair of conjugate embeddings, you just take one. Why is this important? because actually given a curve with complex multiplication, we have in a natural way a CM type. This, we just get it by looking at the axiom of the endomorphisms into the tangent space. So something more about CM types, don't worry, this is maybe a little bit technical, but I'm not going to use it that much. So if you think that is complicated, forget about it. We say that a complex multiplication type is primitive if there is not complex multiplication field K0 contained in our K, such that the reduction of the CM type, sorry, this is K0, is again a CM type for K0. So this is again technical, but we have a nice characterization. So you can forget about this definition and you just can look at the nice characterization that actually we have that the complex multiplication type is primitive if and only if the Jacobian is simple. And this is what we are going to use. Basically because I'm going to work with simple Jacobians. Okay, so these were some definitions that I wanted to give you first. And now we can start to talk about the generalization of the complex multiplication method. So, I mean, the idea is going to be the same. I mean, if we want to construct a curve of genus G with a given number of points, at the end, we just need to construct a curve that has a special endomorphism that is the Frobenius. And then at the end, the problem is to construct curves with the endomorphism ring of the Jacobian, a fixed order in a complex multiplication field. So, I mean, until this is fine, so, I mean, we arrive to the point in which we need this class polynomial, so kind of a generalization. So, I mean, first thing, I mean, look at this. Somehow I try to do the same thing. So, I mean, this time the class polynomial depends on the order, of course. It depends on the complex multiplication type. And then here there is an I. Why? Because actually elliptic curves, they are just defined. I mean, the isomorphism class of an elliptic curve is just given by the J invariant. So you only need one invariant to define it. And I mean, somehow this is a funny thing. We always call it the J invariant. And actually the J invariant is not exactly what we call a curve invariant. It's what we call an absolute curve invariant. I'll give more details about this later. But whatever. The thing is that one elliptic curve is defined by the J invariant, only one value. But if, for instance, we go to genus to curves, the space of the modular space of genus to curves has dimension 3. So you're going to need 3 invariants. So, I mean, this is why I put an I here, because I mean, for higher genus, we are going to need like more class polynomials, not only one. And okay, and then here we need some invariants. Okay, but the question is, which kind of nice properties do we need for those invariants? And well, the first thing is that we need them to be modular ones. What's the meaning of modular ones? So, I mean, in general, an invariant for a curve is you just take the curve, you look at the coefficients of your curve, and an invariant is going to be a polynomial on the coefficients. So, well, I mean, that of course is invariant. I mean, if you consider another isomorphic curve. So, I mean, this is an invariant. But what's the meaning of being modular? Modular means that actually if your curve is defined over the complex numbers, you can also consider like the Jacobian of the curve. This is a principally polarized abelian variety. And I mean, you can look at the Siegel modular forms. And I mean, invariants are related with these Siegel modular forms. So, I mean, maybe this is complicated if you never heard about it. But I mean, the classical example is for the elliptic curve, the thing that you are able to write down the J invariants in terms of tau. So for instance, for genus to curves, that could be the equivalent thing that you start with your curve, you have the period matrix, this gives you a tau in the generalization of the Siegel upper space, and then you can evaluate like some Siegel modular forms that give you invariants for the curve. So we need this kind of modular expressions for the invariants that we use. Then we want absolute ones. So I mean, this is the absolute ones. Actually, the J invariance is not really itself an invariant, it's a quotient of invariance of a curve. So here we have the numerator, the A, when we have the sort Weierstrass model of the elliptic curve, and in the denominator we have the discriminant. Why do we need this? It's very easy. Like imagine that you have a curve, an equation, and now you multiply all the equation by 7. Then you have the same curve. But if you compute the invariants, I mean, the invariants are going to be multiplied by some power of 7. So, I mean, in order to kill this extra 7 or lambda, the multiple that you are considering, you have to consider this quotient of invariants of the same way. this is what is happening for the J invariant. You consider invariance of weight 12. Okay, so you need a quotient. And what should we put in the denominator? The natural choice is the discriminant, because of course you want to put something in the denominator that is not 0. So the discriminant of a curve is not 0. So I mean, this is kind of a natural choice. Good, but then we have a problem that we have denominators. So I mean, these polynomials, they are not going to have in general integer coefficients as we did for elliptic curves. Because I mean, elliptic curves, they are also abelian varieties. So if they have complex multiplication, a theorem by Tate tell us that, well, they have potentially good reduction everywhere. So at the end, you are not going to find any prime in the denominators. But now when you go, for instance, genus to curves, well, I mean, the curves may have bad reduction. Not the Jacobian. The Jacobian is always going to have potentially good reduction, but the curve may have bad reduction, and you may have primes in the denominator, in the discriminant. So, I mean, somehow this is bad, right? Because now the strategy is that we want to approximate those polynomials. But I mean, again, the example that I gave before, 2.99, what is now? 3 or 29 divided by 100? By 10, sorry. Well, that they are like different expressions. So you really don't know. So if you want to still use this strategy, what you need is to bound these denominators. If you have a bound of these denominators, and the strategy of approximating those polynomials works. And well, then once that you have solved this problem, what you need, because what you are going to compute are the invariants of the curve, is like a reconstruction algorithm, as we did for genus 1, that I mean, given the J invariants, we know how to compute an elliptic curve with the J invariant. And well, I mean, actually this for genus 2 is also know how to do it, and for genus 3 is also know how to do it. So I mean, we don't worry too much about this point. Okay, very good. So this is a general strategy. Let's see what is done for the genus 2 case, because actually for the genus 2 case, it's solved. We know how to do it. So a genus 2 curve is given by an equation like this. So it looks a little bit like an elliptic curve, let's say, but this time the polynomial has degree 5 or 6. We do have invariants for these genus 2 curves. They are called Egusine Variants. So I mean, I wrote it like this because they are actually projective invariants. I mean, it's the thing that I said. If you multiply all the equation by 7, then you get some 7s that come up. So you have these for invariants. And those invariants, they admit a modular expression. Was Igusa again who gave these modular expressions for those invariants. And I mean, we can consider these absolute invariants. So I mean, this I10 is actually the discriminant of the genus 2 curve. So I can consider, for instance, those combinations. So basically I put in the numerator since with the same weight that in the denominators. And I mean, I have always the discriminant in the denominator. So what we need now, well, to bound these primes, those denominators, this is what we need. So what we need is to control the primes of bad reduction of the genus 2 curves. And I mean, this is done. I mean, actually was not trivial at all. Here I'm writing like 5 names, but I mean, actually there are a lot of papers that at the beginning it was Goren and Lauter, and there are 2 or 3 papers on this topic. There's then Brunier and Young, then Ollion, then Lauter and Pirae. And I mean, after 5 or 6 papers, they managed to completely understand like the primes appearing here and the exponent at which those primes appear in the discriminant. I mean, this was not trivial at all. So, I mean, the main idea, I'm giving it very fast because I'm going to reuse it a little bit for genus 3, is that if you have a prime of bad reduction of your curve of genus 2, then the reduction of the curve has to be the union of 2 elliptic curves. And this implies that the Jacobian has to, the reduction of the Jacobian, sorry, here I forgot a bar, has to be isomorphic with the product polarization to this product of elliptic curves. So, I mean, in this way, you get what they call a solution to the embedding problem, that is an embedding of the order that you have complex multiplication by into the endomorphism ring of these 2 elliptic curves. This is going to look a little bit like matrices with entries of the matrices in the endomorphism ring of the elliptic curves. So the idea is that what they do is that they manage to give a formula for the number of embeddings that you have here, and then, I mean, to relate these with the primes that appear here in the denominator and the exponents. As I said, not trivial at all. So yeah, they prove this, that you have bad reductions, so a prime in the discriminant, if and only if you have a solution to the embedding problem. So, I mean, we are going to try to do this for genus 3, but here there is an important thing that is going to make things more difficult for genus 3. That is like, well, we are working with simple Jacobians, so complex multiplication type primitive. And in genus 2, this is easy to characterize. This just by looking at the field, you know how to characterize it. You have it is primitive if K does not contain any imaginary quadratic field. And I mean, unfortunately for genus 3, it's going to be more complicated to take care of this thing. Okay, so let's go with the genus 3. So now, even more difficult still for curves of genus 3, I mean, we have two options. They may still be hyperelliptic, so they are still given by an equation of this form, but they may be also non-hyperelliptic, so they are given by plane quartics. Oh, sorry, this is equal to 0, obviously. I was thinking on the 4 of the degree. So they are given by an equation like this. So we have kind of two families of genus 3 curves. Well, we have invariants for those families. So for hyperelliptic curves, we have the pseudo invariants. And I mean, last year in a paper, I gave a modular expression for those invariants. So, I mean, this is good. For the plane quartics, the non-hyperelliptic ones, we have the Dismeron invariant. So we also have nice invariants. And we also have a modular expression that was given by Garcia and Ritz and Thaler also last year. So, well, we have nice invariants. We can keep going. What is happening now? Well, for the absolute version, yeah, sorry, I mean, I took a picture because I realized in the last moment that I wanted to add this image and I didn't have the time to do it nicely, but I hope you understand. Now I will explain. So, I mean, we are going to consider absolute version of those invariants. So, I mean, the same idea. In the numerator, we put some invariants, and in the denominator, we put a multiple of the discriminant. So, I mean, with all my co-authors, we proved in a paper 2 years ago that in the case of hyperelliptic curves, when you do this, you put the discriminant in the denominator, then you only have primes of bad reduction in the denominator, which is good. But then with also Garcia, Ritz and Thaler and Liu, we also proved that in the case of plane quartics, so the non-hyperelliptic ones, when you put the discriminant in the denominator, you have primes of bad reduction, but you also have primes of hyperelliptic reduction. And those ones, we still don't know how to control them. And I mean, I could give a whole different talk about this hyperelliptic reduction thing, so I'm not going into the details. So, I mean, a little bit, and I mean, this is why I put it this picture, is that if we consider A3, so the principally polarized abelian threefold, then in general, what you get is a Jacobian of a genus 3 curve, non-hyperelliptic one. But then here, Chi18 gives you the locus of hyperelliptic Jacobians. And then when you intersect this locus with the locus of sigma 140 equal to 0, then you get the principally polarized abelian threefolds with the composable polarization. So those ones, they are not Jacobians. They are just the product of bad things. So, I mean, a hyperelliptic curve that is here, the only way in which you get bad reduction, I mean, is with this the composable polarization. But if you are outside, you are here, oh, sorry, you have a plane quartic, then you may fall down in the decomposable case, so bad reduction, but you may also fall down in the hyperelliptic locus. So, I mean, it's kind of more complicated. But, well, don't worry. We are going to work with the primes of bad reduction that for the hyperelliptic case are precisely the primes that appear in the denominator of this class polynomial. So, I mean, the good thing is that we have bounds for those primes of bad reduction. And this is something that we actually got, like, I mean, this is the first paper. I mean, it's nice. The N here is Rachel, that is here. And the M here is Michelle, that I don't know if she's here today, but she was yesterday. So, I mean, this was a first paper in a Women in Numbers conference, in which we gave a first bound for the primes of bad reduction under some assumptions. And then this was a follow-up paper in which we finally were able to get like the bound for the, well, a bound for the primes of bad reduction. And well, yeah, this bound is a little bit big. So, I mean, it's not that practical. And of course, we have the thing that we still need to bound the exponents. So not only a bound for the primes, but also a bound for the exponents. And I mean, this is going to be read as follows. So, I mean, how many curves has bad reduction at P is going to be read by how many solutions we find to the embedding problem. And then the how to bound the exponent, so with power in the discriminant appear this prime, is going to be measured by the solution, how it looks like. So, I mean, this is what we want to do today. So before I go to the algorithm to do that, let me say that we have like an extra problem. So I mean, this complex multiplication method is not that easy to generalize for genus 3. There are like many new problems coming up. And one problem is that actually when I was talking about saying, yeah, so we get the class, we have the invariance, blah, 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 blah. Well, the problem is that when we start with a complex multiplication order, and we say, okay, which genus 3 curves have complex multiplication by this order, we don't know if they are hyperelliptic or non-hyperelliptic. So we don't know which invariant we have to use. So this is like an extra problem. And even, I mean, I saw examples, Jeroen Seislin provided them, of orders for which indeed you have some genus 3 curves with CM by this order that they are hyperelliptic and some of them they are non-hyperelliptic. So I mean, you really have to look at the different orbits. So I mean, this is like an extra problem that we don't know how to deal with it right now. But for instance, I mean, sorry, in this paper by Onika, one of my co-authors, and Dina, her PhD student, they implemented an algorithm like using these class polynomials in the case in which I is in the order. Because if I is in the order, then in this case, we know that all the curves are hyperelliptic. And then we can use all the machinery that I introduced. Okay, very good. So let's go to this embedding problem, how to control these primes of bad reduction. So we start with the curve of genus 3 that has CM by an order in a complex multiplication field. We ask the CM type to be primitive. This is that the Jacobian is simple. And we take a prime of bad reduction. Then we can prove again that the reduction of the Jacobian has to be the product of an elliptic curve and an abelian surface. This is because the polarization becomes decomposable. And we have a polarization that looks like this. We can prove, because I mean, we need to have like a, this is the endomorphism ring of the Jacobian, in our case is equal to the order. And then there is an injection, an embedding into the endomorphism ring of the reduction of the Jacobian. That is this endomorphism ring. So because we have this embedding, and this is something that is big, rank equal to 6, this implies that A actually has to be isogenous to the square of the elliptic curve, because otherwise you wouldn't have enough endomorphisms here, and moreover that the elliptic curve E has to be super singular. So this is a first thing that we can prove. Now we define in an equivalent way as it was done for genus 2, what is the embedding problem. I'm adding this adjective, the name, reduction embedding problem, because I'm going to define actually 2 embedding problems, you will see. So the embedding problem, the reduction embedding problem, the rep, is going to ask for the following. I take an order in a sextic CM field K, I take a prime of bad reduction, then the problem asks to find a supersingular elliptic curve E, a principally polarized abelian surface A with polarization lambda A, an embedding like this, and such that the Rosat involution induce complex conjugation on O. So I mean, this last condition is again a technical condition. But the idea is that now when we have a curve of bad reduction at a prime P with complex multiplication, then this bad reduction implies that we have a solution to the embedding problem. So in order to control the bad reduction, what we are going to do, or what we want to do, is to compute this number of solutions. The problem is that if I tell you, okay, so tell me how many solutions do I have for this? This is like super difficult, right? Like, I mean, we don't know how A looks like. We know that it's isogenous to E squared, but I mean, and how do you describe this endomorphism ring? So the idea now is that we are going to be we are going to go a little bit further, and we are going to use like explicit isogeny to do something. So this is the thing. I'm going to call R the endomorphism ring of the elliptic curve, the supersingular one. So this is an order in a quaternion algebra. I'm going to fix an isogeny, let's say of degree n, between E squared and A. Then, starting by a solution to the rep, as I had here, I can conjugate by S with the isogeny and the dual isogeny, and I can get an embedding into here. So these are matrices of side 3 entries in the endomorphism ring of the elliptic curve, E, but I mean, I have a denominator that is coming because I'm conjugating by S, and S doesn't have an inverse. It's like the dual divided by N at most. So I get this. So this motivates a definition, the isogenous embedding problem. This is going to ask to, okay, again, given the order in the sextic CM field, given a prime number P, we need to find a supersingular elliptic curve E with endomorphism ring R, a degree n square polarization, lambda, and an embedding like this. And well, again, the condition that Rosati involution induced complex conjugation. So, okay, this looks nicer, right? Because, I mean, we are going to prove that, I mean, given a solution to the rep, we can construct a solution to the YEP. And are those solutions to the YEP the ones that we're going to try to construct explicitly with an algorithm? I mean, this look easier, right? Because now the R is an order that we know, these are just matrices, so we can try to construct them. So, I mean, as I said, a solution to the rep will give us a solution to the YEP. So are those solutions to the YEP the ones that we want to control? So for this, I'm going to fix a particular isogeny. How can I do this? The idea is the following. So I need a little bit more of notation. So I take the field K, the complex multiplication field. So it is an imaginary quadratic extension of a totally real field. So I can write it as Q of a square root of minus mu, where mu is in the totally real part. So a degree 3 totally real field. And I call eta actually this square root of minus mu. So eta satisfies in general an equation like this. Now I start with a solution to the rep. So I have something like this. And I look at the image of mu by iota 0. So I get a matrix. Well, a matrix. X is an endomorphism of E. Y is a homomorphism from A to E. Z is a homomorphism from E to A. W is a endomorphism of A. So, I mean, it's not really such a matrix, but well, we have something like this. So, I mean, in this previous paper, I mean, it was a small variation of instead of mu, we took eta, but we can do it with mu. I mean, this time we do it with mu because we saw that for the algorithm is better. So it is more efficient if we consider mu. So thanks to these elements that we find here, we are able to define a homomorphism from E squared to A. And indeed, we managed to prove that it is an isogeny. So starting with this with a fixed solution to the rep, I'm able to construct a particular isogeny, S. Now I can conjugate by this isogeny S, and then I get a solution to the YEP. And the image of this solution to the YEP, for mu, it looks like this. I mean, this part is nice because, I mean, the S is constructed with some pieces of iota 0 of mu. So when I conjugate, I get some nice relations. And then iota of mu is an ugly thing like this. So basically, if we want to compute solutions to the YEP, so solutions like this, we have to find the image of, oh, sorry, here is eta, not mu. So I'm looking for the image of mu and the image of eta. So I need to find these x, a, b, c, d, x1, x2, etc. But of course, they have to satisfy some conditions. Which conditions? Well, I know that, I mean, iota of mu is an homomorphism, so it has to satisfy the equation that mu satisfies. So it has to satisfy this equation. Eta is a square root of minus mu. So here is mu and here is eta, but well, we have a relation like this. And then we have the condition on the Rosati involution and complex conjugation. So we get more conditions like this. So, I mean, I'm not giving like all the details of all those computations, but with all this, we can prove the following. First, that X and A, I can go back for a second. So X and A are the two elements here. So they are in those intervals. So, I mean, A and B, capital A and capital B, we know them because they are the ones defining the minimal polynomial for eta, so for the complex multiplication field we are working with. So X has to be in this interval. Once that we know X, so I mean, this starts to look like an algorithm. Once that we know X, we can compute A because we know that it's in this interval. Now, because all the relations that we compute with those equalities, we know that D, C, B, gamma, N, all those are given by those expressions. The Xi actually only depends on X1, X2, and X3, and they have trace equal to 0. And then we get 3 extra equations relating the norm and the traces of these elements. So with this, we can start to do an algorithm. And this is what we do. So, I mean, this is kind of the algorithm. The algorithm is that we give an order in a Stixian field, a prime number P, a supersingular elliptic curve. So, I mean, this is just given by the order in the quaternion algebra. And then the output is that we get like all the solutions to the YEP that looks like this. So the idea is that first we compute like the possibilities for the image of mu. So recall that that was a matrix that depend on all those parameters. So this we can do it, I mean, with a loop. So we try for all X, for all A, and I mean, we compute all the relations that we had before. Then we compute the image for eta, that it depends only on X1, X2, and X3. So we compute all the options and we add that. Then we have this part of check if it leads to O, is because actually with this we are computing an embedding of set of eta and mu, but maybe the order is a little bit bigger. So I mean, we have to check that this embedding leads to the full order. Then if K contains an imaginary quadratic field, we still have to check the primitivity, and we don't always know how to do this. So I mean, we are overcounting solutions. So, well, yeah, we could be overcounting solutions because we don't completely control this primitivity thing, but we get a bound for the number of solutions. And I mean, then we count them up to equivalence. And this is the algorithm. And I mean, actually the algorithm now, it works pretty well, like, well, in a reasonable amount of time. By the first version of the algorithm, it was so slow. I mean, now it looks like easy in the way that I explained it to you, but it took like 2 years or 3 years to get something that worked and that's computed what we want. So yeah, we are pretty happy about this algorithm right now. So there is even a better improvement on this algorithm. So I mean, I think that I still have some time, so I'm going to say a few words about this improvement. So in the case in which we have I or a 7th root of the unity in the order, so the cases in which we have extra automorphisms, we also have this case in which we have a 3rd root of the unit in the order, but then this case, we know that corresponds to Picard curves. And I mean, Picard curves, I studied them in another paper with Kilitsen and Strem, so I'm not talking about this now. But I mean, in these other 2 cases, the strategy to compute the number of solutions, instead of trying to compute the embeddings of mu and eta, we can just embed mu and the square root of d. So for the image of a square root of d, I mean, instead of the xi, we get the di in a similar way, but now we use the thing that we have an extra automorphism. So, I mean, this means that the automorphism has to respect the polarization. So this means that we may assume d2 and d3 equal to 0. And then we know that it has to look like this. And I mean, this is a multiple of the identity. So a priori, you cannot have this because this gives you a contradiction with the primitivity of the complex multiplication type. The only case in which you could have this and still have a primitive type is if you have that the prime p divides the degree of the isogeny. So, I mean, this means that in this algorithm, in this moment, so I mean, until this moment, you don't need to use the prime p. You start to need the prime p that you put in the input here. But now, I mean, in this case, if you know that the prime p divides n, then you can just run the algorithm until here, and you check the primes that divides the n for the solutions that you found. And then this makes that the algorithm is super fast. And even, I mean, you don't have to run it for each different p. You run the algorithm once and you get all the solutions for all the primes. So, I mean, for those cases, like in a few seconds, you have all the primes of batch reduction. And I mean, you could say, okay, yeah, but this is like a very strong condition, right? Well, yes and no, because somehow I said, I mean, the condition I in the order is a nice condition because it means that all the curves with Cn by this order are hyperelliptic. And then we know which kind of class polynomials we can use. So, I mean, actually, this is kind of good. I mean, for those cases, it works pretty well. So yeah, before showing the examples, that is a nice thing, I want to tell you a little bit more about the theory. So, I mean, we proved that batch reduction gives a solution to the rep, a solution to the rep gives a solution to the YEP, our algorithm computes solutions to the YEP. But now the question is, okay, and do we have the converse? Like all the solutions that you find, can you go back? And it's kind of complicated, actually. I mean, again, the conclusion is that we're going to get a bound, so it's good. And I mean, with the examples, the bound we see that is pretty good. But what is the problem? Actually, the problem is that when we do we know how to do it by hand. I mean, if we start with a solution to the YEP, by hand, we can compute an embedding of O into the homomorphism ring of E times A. So we can compute a explicit A with a explicit polarization, and we can get something that looks like a solution to the rep, but we are not able to prove in general that we can get rid of this denominator n. I mean, case by case, we can compute and we can check it, but we cannot prove in full generality that you can always get a solution to the rep from a solution to the yep. But well, for a particular case, it works. And then we have the thing that, we have a solution to the rep, do we have a curve with bad reduction at that prime? And I mean, actually, in one of the papers by Goren and Lauter, they already proved, at least in the case of a maximal order, and in general, that yes, you can go up. You can get something in characteristic 0 with complex multiplication that has bad reduction at that prime p. The problem now is, again, the primitivity of the complex multiplication type. We don't have the control, the total control for this. So it may happen. So I mean, once that we have a solution to the rep, we have an abelian threefold that the reduction modulo p produced this solution to the rep, but we don't know if this thing was, for instance, non-simple. So, or even if the polarization was not decomposable. So, well, anyway, this is we get a bound, and this is what is important. So now I show you the examples. I mean, we did more examples, so you can ask about this later. Now I want to show you only hyperelliptic examples, but I mean, we have other examples. So over the rational numbers, actually, there are only 8 genus 3 hyperelliptic curves with CM. I mean, I numbered them from 1 to 8. They correspond to some complex multiplication fields. I'm writing here the minimal discriminant for those curves. Well, I mean, that means that for each prime, I look at the minimal exponent that I can find for a model of the curve. So those are the primes of bad reduction with the exponents. And those are the solutions that we find. So, I mean, this is good, right? For the first one, we get a 7 and 11. And I mean, I say that we run the algorithm for all the primes until the bound that we got in the previous papers. So, I mean, those are the only primes of bad reduction that we can have, really. So, yeah, we find the 7 at the 11, that's good. The 3, that's good. Nothing, nothing. The 3 and the 5. Okay, first problem, we find a 47 here that is not here, a 23 here that is not here, and many other primes here that they are not here. What is happening? Actually, it's nice because first we saw this and we said, oh, no, the algorithm is not working. And actually it is working and pretty well. The thing is that actually for those first 5 curves, if you fix the complex multiplication field, you only have 1 curve with CM by then. But for these 3 last one, actually there are 4 curves that they have complex multiplication by this order. Only one that is defined over the rational, but then 3 conjugated 1 defined over a field of degree 3. So when you look at those curves that I call them cubic, because there are 3 of them in a cubic extensions, and you compute the discriminants, then you find the extra primes that we were finding here. So, I mean, this is really, really, really nice. And I mean, it was like the support that the algorithm is good and is well implemented, that it was really hard. So, I mean, this is really, really, really nice. Okay, but somehow this is still only like the primes of bad reduction. And the question was, what about the exponents? How can I recover these 24, 12, 8? Or how can I bound them? How can I control them? So for this, well, I give an explicit example because I'm going to use it later. First, so I take the curve number 1. Actually, we know the equation in this case. So it's given by this equation. The CM field is given by this eta that satisfies this polynomial relation. So those are the capital A, B, and C that we input in the algorithm. And I mean, it has only bad reduction at 7 and 11, as we saw. And here I'm showing to you like the solution that we find for the prime 7. So, I mean, this is the image of the solution. This is the polarization. The reduction, actually the A is the product of 2 elliptic curves. And I mean, this is the solution to the YEP, and this is what we compute with the algorithm. And this is the solution to the rep. This we do it by hand, we lift it. And again, this is the isogeny that we get between A and E squared. And I mean, this is a precise image. So I mean, this is just for showing to you that we can do things very, very explicitly. Okay, but now the question about the exponents, that, I mean, that was the difficult part. So, I mean, for stating that, first I need like this kind of, this is in a paper by me from last year. So we have a Jacobian of a complex multiplication hyperelliptic curve, genus 3, and we have a prime of bad reduction for the curve, but it's going to be of potential good reduction for the Jacobian. And then we can look at the theta constants of the Jacobian. So maybe you don't know about theta constants, I don't know, but I mean, in general, when you have a genus 3 curve, you can attach to them 36 theta constants. And I mean, those are some elements, numbers that they are related with the two torsion of the Jacobian, if you never heard about them. And I mean, in this case that you have complex multiplication, actually, and you have bad reduction of the prime P, it has to happen that 3 of these theta constants have positive valuation B2, another 3 have non-negative valuation, eventually 0, B1, 2 of them have valuation B1 plus B2, 1 of them has valuation infinity. I mean, this is because we have a hyperelliptic curve, so it means that 1 of them has to be 0. If this is the first time that you heard about this, you can forget about this technical part. If you know a little bit, this is nice. And moreover, we get that there exists an integral model of C with the valuation of the discriminant equal to 12 times B1 plus B2. So, I mean, if some of you knows about cluster pictures, that now is something that is very, very cool and many people are talking about this thing. If you look at the 8 ramification points of the hyperelliptic curve, what's happening is that you have a cluster here of 3 points that modulo P to the 2B1 are equal, and 3 that they are equal modulo P to the 2B2. And well, I mean, this gives you, if this one is equal to 0, there is a possibility you get that the reduction is an elliptic curve and a genus 2 Jacobian. And if B1 is positive, then the reduction corresponds to 3 elliptic curves. And I mean, the funny thing with this thing is that actually this B2 that appear here and that appear here and that helps you to bound the evaluation of the discriminant is the last exponent for which the reduction of your Jacobian modulo P to the V2. So yeah, I'm talking about abelian varieties defined over ring and not over fields. That is again a technical thing. So I mean, this V2 is the last exponent for which the reduction of the Jacobian is isomorphic to the product of an elliptic curve and abelian surface with the product polarization. So I mean, this V2 that appear here satisfy these conditions. And this is going to help us to measure this exponent, B2. The idea is that if your Jacobian is isomorphic to this product for an exponent E, then we still have an embedding, a solution to the YEP, but with entries instead of than R, in R, the order in the quaternion algebra, into the endomorphism ring of an elliptic curve with complex multiplication modulo P to D, such as the reduction is the reduction of the elliptic curve we were looking for. So what we need to control is this thing. But actually someone else was taking the control about this. I mean, was interested in this question. And Gross, that was already mentioned today several times, proved the following. If we have a complex multiplication curve, E over a number field M, such that the reduction is supersingular, if we call O the endomorphism ring in characteristic 0 and R in characteristic P, then those intermediate endomorphism rings are given by this formula. So they are like a composition of the endomorphism ring in characteristic 0 and P. So basically the idea is that we are computing solutions to the YEP. So we have to compute the maximal exponent that we can still lift the solution to a solution like this. So this is going to give us a bound for the V2 and then a bound for the discriminant of the hyperelliptic curve. So this is an example. I continue with the example that we had before. So this is the solution that we get for the rep. So basically we have here this element, the -3 plus g divided by 2, and we have I here. So we need to find the maximum V2 such that these two elements are in here. With, I mean, the order in the quaternion algebra is this one. And well, this is not difficult to compute. We compute that this V2 is equal to 1. So this gives us, with the previous proposition, that the valuation of the discriminant is smaller or equal than 24 P2. B2 we said that is equal to 1, so 24 So the evaluation on the discriminant is smaller or equal than 24. And look at the table. This is precisely the 24 that we find here. And I mean, we did the examples by hand, and I mean, we recover like all the bounds that we have for all the exponents in here. So yeah, it really works. Okay, so this is all. Thank you very much for your attention.
Thank you. Fantastic. Questions for the speaker? So I have a question. I'm not sure how. So you mentioned, I think it was there are 8 hyperelliptic curves with CM of genus 3, right? And so if I understand right, and please correct me if I'm wrong. So these were known, and you computed the primes of bad reduction associated to each of them. Is that right?
Yeah, actually, yeah.
Okay, so how hard is it to compute the curves and their equations in the first place?
Yeah, actually, I mean, this is an excellent question because there are a lot of things behind this thing. So those equations actually, so I mean, first it was in, well, I mean, I think that for hyperelliptic curves was already known, but at least Pinar Kilitzer does it in her PhD thesis. He computes all the orders for CM genus 3 curves for which the curve is defined over the rational. So this is a very fine number. So for hyperelliptic curves, there are only these 8. So we knew the fields and we knew the orders, is the maximal order in each case. So then you have to compute the equations. So the idea is that we use like kind of this complex multiplication method. The idea is that we take the invariants, the expression of the invariants, let's say. So we compute them, you get an approximation. And in this way, you say, okay, I think those are the elliptic curves, the hyperelliptic curves. But you are, because you haven't proved it. And actually, right now, yeah, I'm giving to you the equations, but we are not really sure that those are the equations because we didn't have like a bound for those denominators. Somehow, I mean, even if, because, I mean, yes, now we do have the, I mean, at least in the cases that I is in the order, we have the bound for those denominators. So we could do it precisely. The problem is that there is still an ingredient that is missing. That is that when you compute this approximation, you have to control like precision with which you give the tau and the precision that you compute the modular forms. And this we still don't have a control of this precision. I mean, this should be something technical, difficult, but like technical. So we don't have that. But I mean, somehow the thing that we find the primes of bad reduction, precisely the primes of bad reduction of those models, that really supports that the curves were well computed. So, I mean, this is something. And then for some of them, not for all of them, I don't remember for which ones now, but for some of them, there is this work by Jeroen Seislin and so many other people. I think that also John Boyd is here, is in this paper. So, I mean, they give an algorithm for computing the endomorphism ring of Jacobians of curves of So, I mean, for some of those curves, Jeroen told me that he verified with the algorithm that the endomorphism ring is the one that we wanted. So, yeah, let's say that not for all of them we have a proof of the equation, but I mean, we are pretty sure. Like, yeah, let's yeah.
And maybe a related question is that, should it be expected or is it surprising that there are only 8 of them?
No, I mean, I think that I mean, this is what is called the class number 1 problem. Well, the generalization of the class number 1 problem, that for elliptic curves, if I'm not mistaken now, there are only 11 elliptic curves with CM defined over the rationals. For genus 2, I think that there are like 22 or something like this.
Okay, so this is related to finiteness of class numbers.
Yes. Yeah. So you have a finite number. Yeah. This. Yeah, because actually I didn't. Yeah. Well, no. This is the reason. Yes.
Other questions? Okay, let's thank our speaker again.
Well, and I guess that because I'm the last speaker, I have to say that we thanked a lot the organizers for this great conference. Thank you very much.
Thank you. Okay, so the last event then is going to be a forum discussion, and this starts in 12 minutes.